Hello everybody, this is Mike, and today we're going to do another Fusion validation. This one is going to be a beam model. Of course, with Fusion, we don't have the ability to utilize at this time the FEA beam elements. We'll be doing it as a solid model, and I'm going to do it completely from scratch here so that you can kind of see my thought process. If there's anything we need to know as we set up the model, um, special preparation like with this one, it has a load. I think at the center of the beam. It's been a while since I read the problem description. We'll find out here in a minute. So I think we'll need to split that geometry. And the other thing is, it's been a while since we took a look at the version of Fusion. There was a newer version of Fusion released not all that long ago. Today is early September in 2021, and we know the Fusion product updates quite frequently. So let's take a look first of all at the version of Fusion I'm using, just in case there is a difference between results that I get. You try to reproduce it and you end up with something slightly different. We might need to know, whether that's a factor or not. Hopefully not. Hopefully the FEA, presuming that you set up, or two different people or three different people set up the same analyses, in the program, regardless of the version, hopefully it always gives the same result. But just to roll that out so you know where we are, I'm running version 2.0 .10806. So let's take a look at the description of the model that we're going to do. This is a beam guided at one end and fixed at the opposite end. The reference is Rourke and Young, and it's a 16-inch long steel beam with a 1-inch by 1-inch square cross section, a 100-pound downward force at the center of the beam, right? So we'll be splitting that beam so we can apply that load right at the center. One end will be completely fixed. The opposite end allows translation in direction of loading. So when we apply that vertical load, we'll be sure to free up the translation in that same direction at one of the ends. The material we're going to use is an A36. Theoretical deflection is pretty small at negative 0.006827. And then we are given reaction moments at the fixed end. We expect 600 pounds per inch, and at the other end 200. So we can plug in our values at the end here and see how it turns out. So let's go ahead and start with a sketch. And it doesn't matter too much which plane, shouldn't matter which plane you begin sketching on. And it's a 1-inch by 1-inch. So I'm going to type in a 1, hit tab, type in a 1, and hit enter. And then I can finish the sketch and we'll extrude. So if you've ever seen any of my modeling before, I'm not the world's greatest Fusion modeler. My focus tends to be on the simulation end of things, so I'm sure there are people who could do this a lot faster than me. But we need to create the split in the center so we can add our load at that location. So I'm going to select the top surface after selecting sketch, and we'll draw a line there. If I'm not mistaken, as we get towards the center of this, we get an icon right there indicating that we're at the center, and we'll just draw a sketch line across. And because I'm a paranoid person, we'll just double check and make sure that that is, yep, so that's 8 inches. It tells me that adding that dimension would over constrain it, so we'll make it a driven dimension. All right, so that lets us know we're at the center. All right, so we can finish that sketch. And let's go ahead and create a split on the geometry. What I'm going to do is split the faces. So splitting our faces, the split would be the first thing. And I'm just going to go ahead and might as well select all the faces around the perimeter of the model. So that way we don't have to worry too much about the orientation of the model. Once we get into the simulation space, we can just choose whichever face and select our splitting tool. That would be the line. You can see it creates kind of a plane that passes through all those surfaces. It will be split. we'll say OK. So now if I hover over the geometry, you can see that it's been split. Let me go ahead and save this model. And so this is the 8th Fusion validation that I am doing. So let me assign it a name in the location where I save my models. And now we're going to go into the simulation workspace. All right, so static stress is what we want to do for our study type. And we can begin to define our items. So for the material, study materials, the material library, I'm going to make sure that this is set to the Fusion library. So Fusion 360 material library. And then we're going to scroll down until we see the steel. And that was an ASTM A36. All right. And we'll go ahead and say OK to that. All right, so my materials should be defined. If I expand the items over here in the browser, I can see that material's been assigned. Next thing would be the constraints. So one end of this is going to be fully fixed. We'll just select that end. It tells me I have one face selected, and we'll say OK. Now, rotating the model around here a little bit. The opposite end here, I know as my model's oriented, I'm going to select this edge and we'll apply our vertical load in the Y direction. So when we do the constraint here, we don't want it to be fixed. We're going to go ahead and free up the Y translation. So let me go to constraints and we'll select this end and uncheck the UI so that the beam can translate in that direction. So this is the end where we expect to see 200 pounds for our reaction moment, and at the opposite end 600 pounds where it's fully fixed. So we'll say OK to that, and we need to apply our loads, and it's a structural load. We'll select that line where we made the split, and this is going to be a minus 100 pound force. We'll say OK. And at that point, I think we are now ready. Let's see, we have our force there. We have our two different constraints, and we don't have to worry about contacts. I'm going to go ahead and generate the mesh. The default mesh here, I think, is going to be rather coarse. We might get an element through the thickness, yeah. So if anything, if our results are a little bit off, given that we're bending across the thickness of this model, we might want to increase the mesh to improve our results a little bit. But we'll go ahead and run it as is and see how close we can get using the defaults. So let me go ahead and run the solve, and we'll solve it locally. It should solve fairly quickly. And again, we're looking for the vertical deflection, which in our case will be the Y direction. So let's go displacement. And we'll take a look at the Y displacement. So our max Y displacement is 0.006934. Let's go ahead and plug that in and see if we're reasonably close on our displacement. So minus 0.6934. And we're within less than 2% off of what the hand calculation tells us it should be. Now the moment at the fixed end, we're expecting 600. And the way we're going to check that is with the inspect and go to reactions. Then we'll rotate the model around to the fixed end. We can see the fully locked symbol there, right? And that is the moment about the X, right? So let me reorient this a little bit, right? So you can see the X is in and out of the screen, Y is vertical. So this load on here would be causing a moment about the X, and we see a 602.1. We'll round down the 602, and you can see our percent difference there is 0.33, so less than 1% different. that all looks good. And let me clear that. And we'll come over to the end that's not fully fixed and we get a 197.86. Or if we round that up, we get 198. 198. And we're 1% different. If I rounded it down, just to make it a little bit worse, we're at 1.5% difference. So even with that coarse default mesh that we had there, I think that's quite good agreement with what the hand calculations tell us. And hopefully that is an interesting example, quick example, easy thing for you to validate, make sure that the static stress is giving you the correct results in comparison to this predefined problem. So thanks for watching and have a great day.